using inclusion-exclusion as kind of a generalized complement principle to solve problems that otherwise would defeat us. And then talk about the pigeonhole principle as a completely separate principle. It really is on its own. It sometimes gets connected up with other discrete ideas, but sometimes it doesn't. And I'm going to go through examples of the pigeonhole principle starting from the most trivial to some of the more subtle. And that'll be a separate topic, about a half hour at the end of today's lecture. Hopefully we'll be able to finish with that. So what I want to do now to begin my intro to inclusion-exclusion is go back to Chris's question yesterday. Chris said, yesterday we talked about putting distinct objects into distinct boxes. It was this kind of a problem. Let's say we have $5 bills. In each one, we can buy a cookie, and there's two types of cookies to buy. So we want to distribute our $5 bills into either cookie box 1 or cookie box 2. This is equivalent, remember, to let's repeatedly select 5 cookies from 2 types. Same problem. Distribute 5 single dollars into 2 distinct boxes, cookie 1, cookie 2, or choose as 5 cookies from 2 types of cookies. Same problem. Here's another way to look at it. I have 2 numbers, x1 and x2, and I want these to equal 5. Okay, this will be cookie 1, this will be cookie 2. So how many solutions are there to this equation? Yeah, Rob?
Are you building up to the dollars being distinct from each other or non-identical if those don't mean the same thing?
No, I'm not going to build up to that.
Isn't that distinct objects, distinct boxes, when the boxes are not identical and the dollars are not identical?
I meant non-distinct into distinct.
Oh.
I'm already non-distinct.
Okay.
I said it wrong. Thanks, Rob. Now I got to go back and make sure I said it right or wrong. Sorry. This is distributing non-distinct objects, the dollar bills, into distinct boxes. The same as selecting with repetition this many items from this many types. Thank you. I said it wrong. Now I said it right. There is distinct into distinct, but that was before. That was a generalized permutation. That's not this. Okay, questions? Right. It's also the same as the number of solutions to this equation. Choose a number for cookie 1, choose a number for cookie 2. They have to add up to 5. And we solved this yesterday. This is not new. We did this. And we showed that what we're really doing here is taking $5 bills and dividing them into 2 parts, right? And to do that, to divide them into 2 parts, we put a little squiggle sign. And that squiggle sign could go anywhere. Here, 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 here. And I think that's what made Chris ask the next question. Now I'm going to change this. There's 3 kinds of cookies. So now I get 2 squiggles. Okay? And I'm going to write down all the different ways I can do this. There's 10 of them. So I got here my $3. And I'm going to divide these into 3 different parts. Here's the first way I can divide them. That means 0, 0, 3. Okay? Here's the next way. Here's the next way. Here's the next way. Okay, those are 4 ways. There's more. Let's write a few more down. I'm doing this in a very particular order. I'm starting with them both at the left, and then I move the right one over one at a time. And then when I use all those up, I'm moving the left one over one, and then I'm moving the right one over one at a time. So what's left? X, X, squiggle, yes. Squiggle, X. X, X, squiggle, X, squiggle. X, 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 squiggle, squiggle. It's the discrete math dance that Jeff Radcliffe was doing before.
Jonathan made that 3. Should that be a 3 up top, or am I not understanding something?
$3, 3 cookies. equals 3. You are understanding something.
Surprise.
Thank you. How many altogether? 10. We worked this through yesterday. It's $3. That means 3 x's. 3 different cookies, so we're going to divide these into 3 different areas. That means we need 2 squiggles to divide it up into 3 different areas. So it's 3 plus 3 minus 1. Choose, and then we get to decide where we want to put these 2 squiggles. 5 places, where are you going to put the 2 squiggles? We can put them in the first 2. 1 and 3, 1 and 4, 1 and 5. It's 5, choose 2. And the general rule is this plus this minus 1, choose the number of cookies minus 1. Okay, this is what we did yesterday. This is review. Other questions about it? Teresa?
Why do you need to keep those 2 squiggles together? Why is that?
Because this represents having none of the first cookie, none of the second cookie, and 3 of the last cookie. Right, right. It shows that there are none in the second category. And this represents 1 of the first cookie, none of the second cookie, 2 of the third cookie. And actually, that's going to get right into Chris's question, and we'll get in a second. Yeah, Gary?
Is it just coincidence that this looks like a triangle number?
No, it's not coincidence at all. I mean, this is something choose 2. So something choose 2, you know, is always triangle numbers. It's the first one with all the rest. That's 4. Okay, and then you can't use that one again, so it's the next one, which there's 3 choices with all the rest, and then 2 and then 1. So it's not coincidental. No, it's completely because of that. All right, so the answer is 10 here, but Chris asked this question. He said, look, it seems to me that, you know, say you have like 8 of these dollar bills, 1, 2, 3, 4, 5, 6, 7, 8, and if you want to divide these into 3 parts, you really just want to insert a divider into one of 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And if you want to insert 2 in there, then it's 9, choose 2. Here's 1. Here's the other one. There's only 9 places you can put it. And then he said, oh, and I'll handle the situation where you have these 2 together. I'll just, you know, say I'll put them on top of each other. Right? So Chris said, how come that isn't a good way to do it? And the truth is, it is a fine way to do it, but if you count how many ways there are for Chris to do that, it turns out also to be 10 choose 2 and not 9 choose 2. And it's specifically because when he says let's double them up, that adds possibilities that he already has not counted yet, or he already has counted yet. Let me show you. Let's look at this and convert each of these to Chris's notation. So I'll check the ones that looks exactly like the way Chris would do it, or I'll circle them. This one. These look exactly like the way Chris would write them. They're exactly the same as the way I wrote mine. The ones that look different are these. Now, if Chris is choosing 2 spots out of, how many spots are in here? 1, 2, 3, 1, 2, 3, 4. 4 choose 2. He's got 6 different ways of choosing those 2 spots. And here they are. These are all of Chris's possibilities if he counts 4 choose 2. So all of these, where he counts this and puts them double, are situations that have to be added and counted separately. So what Chris is really saying to do, he's saying, I want to count it this way. And I'm saying, that's fine, Chris, but then you have to do, call this n. You have to do n minus 1 choose 2 plus n. And that's the same as just n choose 2. Does that make sense? Okay. Right. And you would see this even more if you had more dividers. With more dividers, suddenly there's a lot more that you've missed, or that you haven't counted, or that you've counted twice in some way. Because these wouldn't be in yours at all, and you'd have to add in a lot more. It wouldn't just be n you'd be adding more of an n squared calculation. So if you counted it your way, the calculation would be much more complicated, but you could get the right answer. And it's probably better just to think of it this way. And that's why everybody thinks of it this way. Is that good? All right. So this is going to lead us to the next question. Here's the same kind of problem. You got 3 different cookie jars, and you want to buy a bunch of cookies. Each one costs $1, and you have $8. So you want to take your $8 and split them into 3 different categories. But, well, let's solve it first. Let's solve it if we don't have any constraints. What would the answer be?
10 choose 2.
8 plus 2 plus 1 less than this, that's 10. Choose 2. There are, 10 choose 2 is 10 times 9 divided by 2. 45 different ways of filling in these x's. 8 plus 3 minus 1, that's 10. Choose 2. You have 8 x's, 2 squiggles. How many different ways are there to put those squiggles in the 10 places? This many. But now I've added these 2 constraints. This does not make the problem much harder. Let's think about it. If I added these 2 constraints, so it looks like this. x1, x2, x3. And I insist that x1 has to have at least $3 in it. Okay? So here's a dollar bill, and here's a dollar bill, and here's a dollar bill. And x3 has to have at least $1 in it. Here's a dollar bill. If I insist on these constraints, then I start my problem out looking like this. And now the question is, how many ways are there to finish up? Well, now I only have $4. I have no restriction at all on my x1, x2, x3, just like I had in my original problem. So I have $4 and 3 categories. So it's going to be this new problem without any constraints. The constraints are now gone. When you get constraints like this, that xi's have to be bigger than some number, it hardly affects the problem at all. You just add up these numbers, take them away from your total, and do the problem with a new total. So what would the answer be? It would be 4 plus 2, which is 6. Choose 2. And that is 12? 15. 6 times 5 divided by 2. Okay, are there questions about this? Yes, Rob.
Is there anything much different that gets introduced if you had like a ceiling restriction on one of the cookie jars?
That's what we're going to do right now.
Before we do that,
Yes.
can I just refresh my memory why it doesn't seem like we're adding back in our bills that are in x1 and x3. I mean, don't we have to say something about how many choices there were to get those 3 bills into x1 and the 1 into x3?
We do, but there's only one.
Order doesn't matter here.
You don't care what order you put these dollar bills in. You just because they're all indistinguishable. So we only care how big x1 is at the end. So if x1 has to start out at 3 and x3 has to start out at 1, the question is, okay, that's fixed. Well, what can I do from here? And if I did care about the order of the dollar bills, then I'd have to do some counting before I started. Yeah.
In a way, we don't even care how big the stacks are, or we'd have to add them back in. Like we're just calculating numbers of ways. How many possible ways can it be?
How many possible different ways can you give a number to x1, x2, and x3 so that they add up to 8?
So you don't even really have to record that there's 3 and 1 and 1 and 3 before you start your calculation. Because we're not trying to get a...
If I'm going to go on, I don't care. I could erase these and just change that number to 4, and then, right.
If the question is what's the probability that x1 is going to have 6 bills or more,
right.
Then you'd have to keep track, right.
Well, what about if you constrain instead like x1 plus x3 greater than or equal to 4, and then...
That's harder.
Yeah, so you cannot do it the same way as...
No,
right?
no. We're going to do something that's kind of just what Rob asked a second ago, and he said, what happens if it's less than something? We're going to do examples of these. It's very hard to count directly how many ways there are to find values for x1, x2, and x3 which equal 8 when x1 has to have less than 3. Here's one way to do it. We can just divide it up into cases. If x1 is less than 3, then x1 could be 0, x1 could be 1, and x1 could be 2. Well, if x1 is 0, then we have a problem of 2 variables equaling 8. And you can do that. How many ways are there to split 2 variables to equal 8? You can do that in your head, actually, without even using the formula. There's 9 different ways, right? And how many different ways are there? This is the addition rule, right? Because these are completely disjoint cases. If x is 1, then there are how many for the other 2? If x is 1 is 1, that means you got x2 and x3 have an equal 7. So they're 8, right? And then this one would be 7. So the answer to this you can do in this direct way. 17 and 7 is 24, but there's another way you can do it, and this other way you can do it is going to work for more difficult problems. And it's the complement way. Instead of looking at x1 less than 3, we're going to look at things where x1 is Not less than 3, right, when it's greater than or equal than 3. And they'll just take those away from the total number of solutions. Well, the total number of solutions we know is 10, choose 2. How many solutions are there where x1 is bigger than or equal to 3? We just did that before. If x1 is bigger than or equal to 3, then this turns down to 5, right? And we get 7, choose 2. And that's the answer. And that better be 24. This is 45, and this is 21. So it's the same. Two different ways of solving the problem. Two different principles.
Could you just, my mind blinked for a second. Could you just
Hate that when that happens.
say that again?
Yeah, my friends and I call that a brain fart. Yes. You can still speak. It's okay. You don't have to say excuse me for a brain fart. Right?
Could you just explain that 10 through minus 7, please?
Yes, this is the total number of solutions to this original problem. And these are the solutions where x1 is bigger than or equal to 3. So when you subtract, you get the solutions to x1 less than 3. We did a problem like this before. We did base 10 numbers that have at least one 0. How did we do that? How do we do base 10 numbers that have at least one 0? We did, yeah, Rob?
You took one digit off and then you did a combinatorial on base 9 for the rest.
Exactly, right. We said that here are all the base 10 numbers. Let's subtract off all the base 10 numbers that don't have any zeros in them. The remainder will be the ones that have at least one 0 in them. How many base 10 numbers don't have any zeros in them? It's like base 9 numbers. And that's what we got. That's when you just want to exclude no zeros. That's when you want to have things that have at least one 0. But now I've made it harder. Now I want numbers that have at least a 0 and at least a 1. Why can't I just go ahead and say, okay, well, I took off all the ones with zeros, and now I'm going to take off all the ones with no ones? Why is that wrong? Right, because they overlap. This is an important idea. That's why inclusion-exclusion theorem comes into play. Because the normal complement has no overlap, but sometimes complements overlap. And when they do, that's when you have to use inclusion-exclusion. So let me present this now from scratch as an inclusion-exclusion problem. We're going to solve this by doing all base 10 numbers minus the ones that have at least a 0 and at least a 1. There, that's what I meant. I'm going to take all base 10 numbers minus those that are not the ones that have at least one 0 and at least one 1.
That the same as just
That's the same as this.
at least 1 0 and at least 1 1 without the whole base 10 numbers?
Yeah.
Minus the complement.
Minus the complement of these.
It's just another
The
way
line on top is the complement. Well, if you can describe to me the complement of these, then I could have written that down. But it's not just the ones that have no zeros or... Let's see what it is. This equals all base 10 numbers. You all know this. You can all just do it logically. But remember this from set theory? A intersect B complement equals what? Not A union not B. So now I'm going to rewrite that. Not the first one. This and is intersection, so not the first one, which means it doesn't have at least one 0. That means it has no zeros. Okay, so no zeros or union or no ones. I did that just to remind you that set theory isn't a complete waste of time. I mean, it does come up. It just comes up unconsciously sometimes. We're taking away the complement of this. The complement of this turns an intersection into a union. The reason I'm doing this slowly also is to force you to see that you have to use inclusion-exclusion. Inclusion-exclusion is a way to count things that are union together. It's a way to count things that are this or this or this or this. That's when you get the overlaps. here's inclusion exclusion for two things. If you want to count the union of two sets, it's the size of the first plus the size of the second minus the size of their intersection. Let's use that theorem over here. Base 10 numbers are 10 to the n. How many base 10 numbers have no zeros? 9 to the n. How many base 10 numbers have no ones? 9 to the n. How many base 10 numbers have no zeros and no ones? A intersect B. This and this. That's the overlap. That's the part we counted twice that we need to subtract off. 8 to the n, right. No zeros or ones means you only have 8 symbols left. That's the right answer.
Wait, so no zeros or no ones, you're saying expands out according to the inclusion-exclusion?
A union B. If you want to know how many things are in here,
Well, that is a union, okay.
or is union and is intersection. Right? Well, again, like last time, we could split this up into cases. The cases where, you know, you have two A's and choosing them first. And you could do this directly, but we're going to do it indirectly using the inclusion-exclusion. We're going to get the total solutions, which is what we just mentioned, and subtract from them the complement of our constraint. What's the complement of our constraint going to be? It's permutations of these letters which do have. Right, and that means if they do, the three that go together could either be A, or B, or C, and that's where the inclusion-exclusion comes in. Anytime you use a complement trick, which gives you a union of possibilities, that's when you have to go back and resort to inclusion-exclusion to finish your idea. So I'm going to write down 3 A's, union 3 B's, union 3 C's. And make a note to yourself, because if you look at it later, you'll forget what this means. This means all strings that have 3 consecutive A's in them. This means all strings that have 3 consecutive B's in them, all strings that have 3 consecutive C's in them. A, B, C, minus A intersect B, A intersect C, A intersect B intersect C, thank you, plus so, all right, now you tell me, and feel free to completely argue with my choice here, but would you rather right now have been taught the inclusion-exclusion theorem for the very first time, and then after that side 45 minutes come back to this, or would you have rather already known this when you saw set theory and then just have me do it now? Because I thought it's better to do it before. Right? Now you see it now, right? All right. So this Anthony asks us at the beginning, he goes, well, you know, this is a really good book, and I agree. And you're like, why don't you just like go in the order? Well, I think his choice here just stinks. I think it's just a bad choice. I think he really should have done inclusion-exclusion in the set theory chapter. And maybe in edition 5, if enough people tell him that, he'll move that section over there. But there's lots of situations here where it just isn't obvious where to put the section. And I think here it doesn't belong so much in counting as much as it belongs back in set theory, and then you just refer to it again. Let's figure this out.
Do you need the complement of it?
No, no, no. I took the complement of this. I skipped a step. I took the complement in my head and just wrote this down. It's minus the complement of the things without 3 consecutive same letters. That complement is the things with 3 consecutive same letters. Okay, so I just did that step without writing it down yet. Okay, well, let's do this piece by piece. Let's take this, just this part here, and break it up into pieces. The first piece is the number of things just in this set, the things with 3 A's. How many are there? 6? Remember what this means. This means there's 6 different ways to order 3 A's, but that's not what this is measuring. This is measuring how many strings are there that have 3 consecutive A's in them. What does that mean?
The A's could be in space 1 through 3, space 1.
So it could be in
If there have to be 3 A's coming together, then why don't we glue them together? Just like Baruch was saying. Right, let's think of them as one. So how many items do we have now to move around? 7. And what are the different types? 3, 3, and 1. Good. Isn't it nice to have some tools, to have some ABCs? We wouldn't have known that this was helpful if we didn't know how to do problems like that. But we know, so we can continue to the next step. 3B's is similar, and 3C's is similar, so it's just going to be 3 of these. I've taken care of this part. Now let's take care of the next part. 3A's and 3B's. That means I have only 5 objects. 1 a chunk of A's, 1 a chunk of B's, and then 3 distinct C's that can move around. So I'm going to take 5 objects, and the different types are 3 factorial, 1, and 1. And I have 3 of those possibilities. 1, 2, 3. 3 different pairs of things that go together. Finally, plus, if they all have to be, that means there's 3 possibilities. There's 1 of each type. That's it.
Doesn't seem right. Are there really 6 possibilities to arrange? So they could only be 3.
Yeah, all the A's come first, and then B and C. A, C, B. B. It's like what are the permutations of 3 elements? Exact same thing.
That was where I got my 6.
Okay, right, good. Well, I don't know, did I do the answer here?
No, you did right.
No, but I didn't write the answer down in this problem, so I have no idea what this turns out to be. But this is the right answer. You do this, you subtract off all of this. Keep in mind that this is equivalent to this bracketed part. Okay, that's not the whole thing here. That's just the part after the minus sign.
So the minus goes through that.
So the minus will have to go through that, right. And you're going to end up subtracting this, adding this, and subtracting that. Remember, in this problem, when you have the less than criteria, it's hard to count. If I want to find out the number of solutions to this equation, when each of these has to be less than 1, 2, and 3 respectively, that's a tricky problem. So we're going to do it by complement. We'll take all the solutions to this, which we know again is 10 choose 2. The total number of solutions is 10 choose 2. We want to subtract from that the solutions that don't have this criterion, the complement of these. Now this is supposed to mean ands, right? This, and this, and this. So if I complement it, I get what? Reverse it. So x1 is bigger than, not greater than or equal, but strictly bigger than 1, or x2 is strictly bigger than 2, or x3 is strictly bigger than 3. This is again from the Morgan's law. If I run a not through here, all the conditions change parity, and the ands change into ors. But now I've got a set of conditions that have ors between them. So to count those up, I need the inclusion-exclusion theorem. And that's what we're going to do. Okay so far? Okay. Good. Let's work with this piece. Let's do the A and the B and the C part first. How many solutions to this have x1 strictly bigger than 1? Who remembers how to do that? If it's strictly bigger than 1, that means it has to be at least 2, right? So if there's 2 in there, that means there's only 6 left here that you have to get. So it's 6 plus 2. Choose, I just make 8. 8 choose 2. Now let's do the B case. x2 has to be bigger than 2. What's that going to be? 7 choose 2. Good. And the next one, x3 bigger than 3, is going to be 6 choose 2. Now let's do the double cases. What about when x has to be bigger than 1 and x2 has to be bigger than 2? That means x1 has to be at least 2 and x2 has to be at least 3. That means I have how many left? I have 3 left here, so it's 3 plus 2, choose 2. So it's 5, choose 2. What's the next one? x1, x3. 4, choose 2, right? Minus, what's the next one? 2, 3. That's 3, choose 2. Good. You guys are doing this fast in your heads. It's not obvious. And now finally, we have the case where they all have to be. What's that going to be? 4, 3, 8, 8. Leave 0.
Wait, that's 9. That's 9 used up.
4, 3, 2, 9. Right? So that leaves negative. So this is just a 0. Make this a 0. Everybody agree? There's no way to add up positive numbers to add up to negative 1. So.
Doing that, shouldn't it?
I got a funny feeling about that too. I agree.
Because that's compensating for overcompensation in the second.
I agree. There's something really fishy about this. All right, so now that I can see what I actually did, in all of these is that you see these equal signs here? They really should have been strictly, and these should have been equals, and then I don't think I get this problem, because that's the problem I really worked out in my notes. So I didn't work this problem out in my notes, and I'm not sure if it's going to work out evenly or not. I did work out the problem where these are equal signs and these are strict signs. If I switch them, it just changes the numbers by 1.
But if they're all less
obviously
than...
you can't map. Why did you map it to 0? I mean, you get negative. That's already indication that your setup already is off.
Is messed up.
Right. So, and
well, I mean, I think it's okay. I mean, it means something. How many ways are there? How many solutions to this equation are there that have all 3 of these being true? And the answer is there aren't any.
right. Well, you could see
So?
it way before that. Right?
Oh no, well, we still have all these. I mean, I'm not sure that.
If you look at the statement of the problem,
I agree. It doesn't look like there's any way to get there.
there's no solution to it.
Right. But we just got no solution to this subproblem. We still don't know that the whole thing's going to agree yet.
But there are many
You got the negative number.
results that would have
Shh.
for the intersection of all 3.
I agree. A lot of them would turn out to be 0. Let's go ahead and check this. I'm not sure if it works out or not. It does work out to 0? So 10 choose 2 is going to be 45. Minus, what's this? Read them off. Minus 28 minus 21 minus 15 plus 10 plus 6 plus 3. So hope to God that turns out to be 0. It is. It's 0. Woohoo! There. 1 for the inclusion-exclusion theorem. So this is a perfectly fine way and a perfectly stupid way of doing this problem. If I gave you this problem on the exam and you said, oh, that's an inclusion-exclusion problem, and you just spent 20 minutes like I just did doing it, then you got your brain turned off. It's true. You should just look at this like Baruch said and said there's no way to do it. And you should. But I think it's still a completely reasonable and worthwhile thing to work through this and see that it still works and gives you the right answer, even if it gives you it in a convoluted way. And I will change my notes next time. I'll probably do 3, 4, 5 rather than 1, 2, 3, or maybe not. I'm not sure if this is a good way to do it or not. But I think it's worthwhile. It still works. There's nothing wrong with what we did. We just get an answer the slow way instead of a fast way. You all come in with lunches. You give me all your lunches. I put them in a box. I hand them back out. I'm not malicious. I hand them back out in a random way. What's the chance all of you get somebody else's lunch, that nobody gets their own lunch back? Okay, that's the question. And sometimes written down as the hat check problem. Everybody checks their hats. They're given back randomly by a clueless hat check person. And what's the chance you get your own hat back? What's the chance nobody gets their own hat back? Yeah?
Does this include giving more than one thing to any one person? Like, could you end up giving 35?
No, everybody gets just one lunch back. Except if it's their own, then that counts as a non-derangement. But if it's not their own, if everybody doesn't get their own, it's a derangement. Okay. So there are n factorial ways of me giving back the lunches. It's just a way of ordering the lunches in a row and having you come and pick them up. n factorial ways. The question is how many of them are derangements? How many of them don't give you back the one you want? And we're going to solve this by complement. I'm going to subtract off the ones that are not derangements. Well, which ones are not derangements? Describe them to me in English. What makes a permutation a non-derangement?
At least one person gets their lunch.
At least one person gets their lunch back. So it could be, how do you want to divide these up into cases? Let's divide it up into unions of cases. There's lots of ways to do it. Here's a bad way. One person gets their lunch back. Two people get their lunch back. Three people get their lunch back. Exactly one, exactly two, exactly three. You all exactly get your lunch back. I can count some of those. The chance of you all getting your lunches back is 1. The chance of one of you getting your lunch back. Well, any one of you could be the one that got their lunch back. That's 36 possibilities. And then the rest of you could get your lunches back in any way as long as, the rest of you could get your lunches in any way as long as you don't get your own. But isn't that the same problem we're solving?
For 35.
It's the arrangements for 35. So either we go down this route and make a recurrence equation, or we go another route. We're going to go another route. Okay? This route for the recurrence equation isn't a bad route, and it will teach you a lot of good stuff, but it's the wrong week. So this week we're not going to do it. Instead we're going to divide up the cases differently. Instead of saying one person gets their lunch back, two people get their lunch back, I'm going to divide it up into Chris gets his lunch back. Sharon gets her lunch back. All the permutations where Sharon gets her lunch back. All the permutations where Chris gets his lunch back. Now this seems even worse, because Sharon can get her lunch back in permutations where a lot of you also get your lunch back. So how are you going to add these up? But here we can get the overlap taken care of by the inclusion-exclusion theorem. So let me write down the categories.
Shai?
Yes.
Just typically we actually steer away from, we go from a question of this type to the question where none, where actually one arrangement. Here we are constructing it.
Agreed that you usually, right.
The complement issue is sort of...
Right, usually you like ands, and here you don't like ands. Here ands are hard. You're right. Good point to make. I don't have any comment on it really, except that it's true.
Is that really hard?
It is really hard. Right, you can't, it's hard to count this directly. And this really is the only way people know how to count it easily. Yeah. All right, so let me write this down. I'm trying to figure out the best way to write it. But this is the list of things that are not derangements. So let's say, let me list the people as say P1 to Pn. Those are the people, right? So I'll say P1 is fixed. That means P1 gets his or her lunch back. This means all the permutations where P1 stays the same. Person 1 gets the lunch back. Okay, everyone get that? Union, or P2 is fixed. Or Pn, the nth person, is fixed. We got to add up all the different permutations where this is true, or this is true, or this is true, or this is true. Okay? Let's do it. Subtract all the intersections. Oh, geez. You can all the combinations of pairs plus all the combinations of triples minus all the combinations, etc., dot, dot, dot. Go look this up in the book. It looks just that ugly. It's very hard to describe the generalized inclusion-exclusion theorem. How many permutations are there where I make sure that Sharon gets hers back? I don't give a hoot about what everybody else gets back, but she gets back her lunch. So I got 36 lunches. I look for hers. Okay, an apple and a cheese sandwich. Very good choice. Here it is. And now I got the other 35 lunches, and I can just toss them out any way I want. How many ways are there to do that? 35 factorial or n minus 1 factorial if I started with n. So this is n minus 1 factorial. Does everyone agree? And so is that one. So how many do I got? Yeah, but don't simplify things because you lose the pattern. How many ways were there for me to choose a single person out of you all? I chose Sharon at first, and I found n minus 1 factorial ways. But I could have chosen John. And I could have chosen Donna. And I see Jimmy, and I see... I just want to do romper room. So, I got n choose 1. That's how many different people I can choose to fix. Single people to fix. And each one of those represents n minus 1 factorial permutations. Plus, next row, minus, next row. Now I'm fixing 2 people, and then I don't care what happens in the rest of them. So I can choose 2 people from n and n choose 2 different ways. And then I get n minus 2 factorial. And I do this over and over again, and I hope you see the pattern.
Wait, does P2 mean 2 people are fixed? Or does
Yes.
a different person is fixed?
It means 2 specific people are fixed. Sorry? No, it means person 2 is fixed.
Oh, yeah.
But I'm not up to here. This isn't this.
Okay, we're still on.
This row is this. It means person 1 and person 2 are fixed. Person 1 and person 3 are fixed. So there's n choose 2 things in this row, and each one is n minus 2 factorial. Okay? Sure everybody gets that. N choose 1 things in this row, n choose 2 things in this row, n choose 3 things in this row. The number of permutations with this criterion are n minus 2 factorial. The number with this criterion are n minus 3 factorial, because I fix 3 people and I have n minus 3 choices for the rest of you. I keep doing this until I get to the very last one. Now the last one is either plus or minus, and I don't know what it is, so it depends what n is. If n is odd, it's going to be minus, and if n is even, it's going to be plus. So I write minus 1 to the n, and what goes there? N choose n times n minus n factorial. There it is. N factorial minus this mess. But this mess you can simplify with some algebra. And it simplifies to some really, really surprisingly, really cool answer. And that's why everybody puts this in books, because it's a cool problem that is a cool answer. Sometimes you get one, not the other. I don't know. I don't know about that piece. All right. But here's what happens when you fiddle with this and you factor it all out. What was that? Always happens at that particular time? Let's try to simplify this out. What do we get here? I get n factorial, right? Plus, what do we get here? N choose 2 is n times n minus 1, right? Times n minus 2 factorial. So this is n factorial over 2 factorial. And the next one is n factorial over 3 factorial. Here's what you get. N factorial. I missed one somewhere. What did I miss? I'm probably missing a term at the beginning here. No? I don't think I did anything wrong, but something's wrong. I hate that. Well, let me see what I have so far. Here's what I have so far. I'm supposed to have a 1 here, and all the minuses are going to be shifted over, so that would make this right, but I don't know why I lost my 1 here in front. What did I do wrong? My notes are wrong, too, so...
You have a 1 minus 1 there is what you have.
Where?
Well,
if you actually pulled the n factorial out of what you have up above that.
Yeah, I know. Those cancel. I know.
Right.
I know, but I'm supposed to get an extra n factorial in here that I lost. I don't know where it went. I'm sorry. I goofed it up. But where did it go? I mean, I should be able to. Let's figure it out together. I hate to just leave this undone because it's a nice result. N factorial is all the possibilities minus the possibilities where somebody gets their lunch back. Here the first person gets their lunch back. Here the second person gets their lunch back. Right? And I don't see anything wrong with that.
Wait, the problem is that you've already subtracted this from n factorial, right? If you were still just working inside the...
Oh, right. I subtracted it all. Right. Nothing's wrong. Sorry.
Yeah.
Nothing's wrong.
But...
Right.
Yeah.
Right. Nothing's wrong. I didn't do anything wrong. I'm so happy. I didn't do anything wrong. I just subtracted earlier than I wanted to. This is the number. That's the number of derangements. And if I take that, this is the number of non-derangements. And if I take it away, I get the number of derangements. I think I did it right now. Good. Let's hope. All right, if you actually go ahead and calculate this, here's what you come out to get. And this goes back to calculus, and I won't go through the details. You can check your book for this. If you take the number of derangements and you divide by n factorial, that gets rid of this n factorial in here, you get just this funny-looking fraction. And this funny-looking fraction, as n goes to infinity, approaches 1 over e, or e to the minus 1. And you should kind of recognize why that's the case because of these 1 over I factorials. All right, I'm not going to prove that to you, but you can check your book for the details of the proof of why it relates to E. I still have a bunch to do today, and I need to keep you probably 25 more minutes. The derangements, this is the derangements, everything here. Okay, so if I divide this through by n factorial, I get 1 minus this. It ends up being the same as 1 over e. 4 pigeonholes and 5 pigeons, then one of the holes has 2 pigeons in it. Okay? If I have 5 cards and 4 suits, 2 of those cards are going to be the same suit. Okay? It's one of the key things in that problem set in that magic trick. We're going to do problems with the pigeonhole principle, not because it's a hard principle, but because it's sometimes incredibly deceptive. And these problems are very much on their own. They don't connect back into the other combinatorics, so I leave them in their own topic. But it's just filled with lots and lots of examples where you think you get the idea, and then somebody shows you a proof that uses nothing but that idea, and you just shake your head and say, how did I ever come up with that? And it's cool to see a simple principle being milked to its incredible potential. So that's what we'll do here. We'll start with easy ones. So I've got 1, 2, 3, 4, 5, 6. 6 being the hardest. Here's A. Prove that 2 people in this room were born on the same day of the month. At least 2. That means 1 through 31. Same. We got 36 people in this room, right? There's only 31 possible days. There's got to be a duplicate. Okay, I'm the 4th.
Yeah.
Oh, already? Oh, the exact same. What's the chance of that? That's a different problem. B. See? Only 6. We're done with 1. B. Prove that 2 people in the United States have the same number of hairs on their body. We're going for the whole gusto here. If you count all the hairs on a human body, it's nowhere near 250 million. It's a lot less. There's lots of people in the United States with the same number of hairs as somebody else. What's that? That's comforting, right. And we will have a little political caucus for all of those who have exactly 89,452 hairs in their body and see if there's anything in common with those people. Scary. C. All right, this is going to get a little bit harder. There's an exam that goes from 0 to 100 in score. You can get anything from 0 to 100. If I want to guarantee that 3 people will get the same score, I want to guarantee 3 people with the same score. How many people do I need to take the test? I need to guarantee 3 people with the same score. This is a little bit of an extension of the pigeonhole principle. I have 101 possible values that people can get, 101 boxes. I start throwing people into these boxes, and I'm trying somehow to guarantee 3 people in the same box. To guarantee 3 people in the same box, I've got to fill, in the worst case, 2 people in each box. There's 101 boxes. That makes 202. I can still set up with no 3 getting the same score. The second I put in any number bigger than 202, there have to be 3 people with the same score. So how many people? Anything bigger than 202.
Why 202?
Because we have 101 possible scores, and I can fill them up 2 per score without having anybody get 3 of the same scores, and that's 202 people. The second I add that last person, one of the holes gets filled, too big.
You need 3 people to have the right.
Oh, I see. Yeah.
Okay?
Yep.
Now, this is not a hard problem, but doesn't it make you pause longer than you think you should? It makes me pause longer than I think I should. I mean, I get the answer, but it takes me 20 seconds instead of 2 seconds. These take 2 seconds. So the next 2 are going to be even worse. Next 3. 51 houses on a street. Their addresses are between 1,000 inclusive and 1,099. Okay, so every address on the street is something 1,000, 1,001, up through and including 1,099. 51 houses on the street. Prove there are at least 2 houses with consecutive addresses. Okay, so there's 2 houses that are like 1,007 and 1,008. There's got to be 2 houses with consecutive addresses.
There's 100 total.
If you figure a consecutive address would be
There's only 51 houses. You can't make.
Okay.
yeah.
They're all odd. Make all the addresses odd, and then you know there has to be one even in there.
Okay, so good. So let me describe how to say that idea in terms of pigeonholes. What are the holes here? The holes here are things that contain addresses. They contain pairs of addresses. There are 50 holes. Each contains two consecutive addresses. Okay, the first hole contains 1,000, 1,001. The next one contains 1,002 and 1,003. So I've got holes of consecutive addresses. What am I putting into these holes? Houses. Right? I've got 51 houses. I put the houses into these holes. I fill up all 50 of them. I got one left. There's got to be 2 houses in one of these holes. How do I put the houses into the holes? I look at the address of the house. If its address is labeled on the hole, I put it in there. So I've got 51 houses. I can put the first 50 into 50 different holes, but when I get that 51st, it's going to have to go into a hole that already has another house in there. And those two houses that are in that hole have their addresses labeled on the hole, and the holes contain consecutive addresses. So those two houses will have consecutive addresses. There's a lot of elegance in these arguments because it doesn't say which two houses have. It just shows you that there exist two that have to be consecutive. This is a very slick way of taking a problem that isn't obvious at all how to prove and turning it into a pigeonhole issue. Are there questions about this? Should I do this one again? What do I mean by a network? That means these computers are connected to other computers. Okay, so imagine that each of us are a computer, and maybe I'm connected to Sham and Jacob and Greg, and Joe's connected to Baruch, and Baruch's connected to Teresa. Okay, there's connections. Okay, so n computers on a network, we're connected in some way. I'm not telling you anything about how we're connected. Prove that at least two computers are connected to the same number of other computers. This is also very, very straightforward once you just think about it for a minute.
Wait, what does it mean for a computer to be connected to the same number of other computers?
That means if I'm connected to you and Baruch and Neil, and Sharon's connected to Chris, Peter, and Donna, we both connect to 3 computers. Okay? How do you know there's at least 2 computers in the room that are connected to the same number of other computers? There's n computers in the room, right?
So how many ways?
How many different possible computers could we be connected to? I could be connected to 1 computer. I could be connected to 2 computers. I could be connected to n minus 1 computers. Every single computer in the world in this room could be connected to n minus 1 other computers in the room. So I make a bunch of holes. Each hole is labeled, how many computers are you connected to? How many holes are there? n minus 1 holes. If you're connected to 2 computers, you go in this hole. If you're connected to n minus 1 computers, you go in this hole. But there's n computers in our room. So when I throw them into these holes, one of the holes has 2 computers in it. And those 2 computers are connected to the same number of other computers. This is actually from a graph theory question. Prove that you have a graph with n nodes, that there are going to be at least 2 nodes that have the same degree, the same number of edges connected to it. It's really a graph theory question. Yes, Brian?
I'm just thinking this assumes that all the connections are two-way.
That's right. It assumes, right, there are no directed connections here. Right. This assumes that you just make a wire, and which may not be realistic, but that's the assumption.
And that you're not connected
to yourself. Right.
Because n has to be greater than n minus.
Right. Right. And that you're not if you allow, then we don't include that in the number. Right. Right. We don't count that. Exactly. All right. The next one's the most clever use. This one really is not at all apparent unless you think about it, and even after you think about it, it's not too apparent. But it's an excellent example. I would say there are maybe a dozen good examples of really complicated uses of the pigeonhole principle, most of which are more or less alike. This is a canonical version of one of them. Okay? A lot of them are just like this. If you get this, you'll get the rest of them. So this is F. This is our last one, and after this, I'll take a minute and summarize and finish up. This is what I call a really clever use. Clever. And I got computers here too, so I'm cooking with gas. Going down the baloney trail. A computer goes down. At least one time every day. Okay, you got a computer every single day. It goes down at least once. That's given. You call it our network. Okay, it's during a month. A 30-day month. Okay, only 30 days in a month here. During a month, it goes down it goes down at most 45 times. It can go down 45, but it won't go down any more than 45 times. Once a day, no more than 45 total during a 30-day period. Okay? That's all the information. Here's what we have to prove. Prove that this implies the following. It goes down exactly, not at least, but exactly 14 times in some consecutive period of days. Think about what this is saying for a second before we go ahead and prove it. The proof is not going to be hard, but it will be hard to find if I don't show it to you right now. Let's see what it's saying. It's saying computer goes down once a day. There's no trick. It goes down at most 45 times in a 30-day period. Prove that you can find some consecutive sequence of days, and if you add up the number of times it goes down in that sequence, that'll be exactly 14. All right? So this is not, it is neither obvious nor unbelievable. I mean, this doesn't say all that much. It just means that somewhere in that 30-day period, I can find some consecutive period of days where if I add up the number of times it went down, it's 14. We're going to make a sequence starting from the first day of the month, counting how many times this computer's gone down. Okay? So if it's gone down 3 times on the first day, our sequence would start with 3. If it's gone down twice on the second day, the next number in the sequence would be 5. So if the number of times it's gone down, say, looks like this, then our sequence would be 1, 3, 6, 7, 8, 10. Everyone understand the sequence that I'm constructing? Okay. Now, I don't know anything about how many times it's gone down in each day, except that each day it's gone down more than once. So I don't know much about this sequence.
Each day's gone down more than once?
Once or more.
Okay.
So let me tell you what I do know about this sequence I just described. Boom. The sequence has how many values in it? How many values in the sequence? 30 values. What's the range of values? In the range, the smallest it could be is 1, and the biggest it could be is? It's going to be. It could be 40. It's got to be 45, right? By the time I get to the end, I better have 45. Oh, at most 45. I take it back. But it could be 45 at the end. What?
It's got to have at least 30 and at most 45.
No, it's got to have at least 1 at most 35.
The upper end.
The range of any particular. I could have numbers as small as 1 and numbers as big as 45. This is all I can say about my sequence. I know it's got 30 values. I know if you look at each of the values, they could be as small as 1. They could be as big as 45. And you also know they're going up.
As big as 16. More than 15. Because every other day during that month has to have
Every day a step of 1.
I think they're confused between sequences.
15 is the most you could have on any.
Let's do a sequence. Here's a sequence. 1, 2, 1, 2, 1, 2, 1, 2.
Okay, now do a sequence where the first one's 45. Is that what you're saying?
What is your sequence, Shai? What do you refer as sequence?
This is the sequence of how often the computers have gone down in day 1, 2, 3, 4, 5, 6, 7, 8. And here's the sequence that I'm constructing. 1, 3, 4, 6, 7, 9, etc. The cumulative sequence is what I'm talking about.
Okay, so an element in that sequence
can be as small as 1 and can be as big as 45. Okay. That's all I know so far. Everybody with me? Where are we heading here? Where does it go? It's almost there. I'm going to make a new sequence. All right, here's the number of times. Let's write the sequence down so everybody can see an example. 1, etc. 30 times. Now I'm going to make a new sequence. I'm going to add 14 to every one of these and make a new sequence. What's my new sequence?
18.
I'm adding 14 to each one. Jeez. That's like, am I in the right place?
Either the 39.
23, 24, 26.
Etc. All right, now I've got two sequences. This one's also 30 long, right? What is the range in this one? 15 to 59. Okay. What's the range in all of them altogether? 1 through 59. How many numbers are in these sequences? 60 numbers in the sequence. I could have motivated this a little better to make it seem less magical, but I love the magic of this proof, the fact that it just creeps up on you and then you're done.
Are you gluing those two sequences together?
Yeah, here's one and here's another. I'm gluing them together at the ends. So I got 60 things in my sequence, 59 possible values. That means that if I think of the 59 values as wholes, and these numbers as things I put into the wholes, means two of these numbers have to be identical. I got 60 numbers, I got 59 values. Can any of the numbers in this sequence be identical? No, because they go up by 1 each time, right? You got to go down, the computer's got to go down once each day. This sequence repeatedly increases. This sequence repeatedly increases. I can't have duplicates in this sequence. I can't have duplicates in this sequence. Where is the duplicate going to have to occur? It occurs somewhere here and somewhere here. Presumably, further on here, we'd have a 15, and it would match this 15. Somewhere in this sequence is going to be a number that's the same as this sequence. What does that mean?
It's going to be that 14 times in days.
Why is that? Let's make sure. Let's say that this is the 17th one here is the number 15. Okay? And the first one here is the number 15. Okay, let's say I get a duplicate there. Does that make,
Let's not say it was 17 because that wouldn't be possible. 15 would be the first day.
All right, so let's, you're right, that's a bad example.
Call it 12 or 10 or something.
Let me do it this way. Say the ith day plus 14 equals the jth day. Say that's where the duplicate occurs. That means between the ith day and the jth day, between the jth day and the ith day, we have a number of times the computer's gone down equal to 14. All right? This is a very, very slick proof and comes up out of nowhere. And how do you decide to construct these weird sequences where you get 59 different values and 60 possible numbers and just get that duplicate, and that duplicate's going to be 14 apart, you know, because this problem is constructed backwards. Right? I mean, you start with this and you work your way backwards and then you kind of hide it. But it isn't always obvious to solve a pigeonhole principle problem. And the good news is that they don't come up as often as the standard combinatorics problems. They come up, I'd say, 1 out of 100 times rather than 99 out of 100 times. But when they do come up, they're most often not this really clever, really neat way, but it's almost always you got 5 cards, 4 suits, you got 2 of the same suit. So appreciate the power of this principle. Don't think it's just like nothing, but at the same time, be aware that these really clever versions, they do come up, but not as often as the basic combinatorial things that you'll have to work with. All right, so here's what we'll do in recitation. I'm going to finish up the onto functions. I'll have Tara do that. We can discuss this proof if you're interested. We can discuss any of the problems on problem set 5. I will today make sure the TAs post solutions for 5 and 4, make sure they're up there. And I will make sure that, that I get problem set 6 up there so you can look at it if you want over the weekend. Are there questions?